Hello. Welcome, everyone. Thanks for being here. Let's get started now. So it's a real pleasure to introduce Chiara Spiniello today. Although she's visiting us for this week. Chiara is Italian, obviously. She's from Naples. She graduated there. And in fact, I didn't know she was an Erasmus exchange student here in the island, so she already knows the island. So I also met her in the winter school I organized in the Puerto de la Cruz a few years ago, so that's how we know each other. At that time, she was in Groningen, completing her thesis with Scott Traeger and Leon Kopmans. And fairly recently, I would say, she moved to MPA in Munich, where she's working with Simon White. And she has a short career, but he's become very quickly an expert on the intermix of dark matter and baryons in nearby galaxies, and this is the topic of the presentation today.
Voila, can you hear me? Perfect. Thank you, Jesus, for the nice introduction, and thank you, Alejandro and Nacho, for inviting me here. It's a pleasure to open your new season for the new talk. And as Jesus was saying, I'm working with Simon White at Max Planck Institute, and I'm becoming famous for my XLENS survey, and especially for the studies I have been doing on the IMF, the initial mass function slope. And that's exactly what I'm planning to talk to you about. So I will introduce the XLENS survey. That's a survey I designed that started in collaboration with Leon and Scott in Groningen in the Netherlands. And in particular, I will focus on how to constrain the initial mass function and its low mass end and cutoff mass directly from galaxy spectra of early type galaxies, the most massive early type galaxies in the universe. And then hopefully I will have some time to talk to you about a new project that I started in collaboration with Matteo Barnabe at DARC, Copenhagen. That is again about IMF, and it combines strong gravitational lensing with stellar population analysis and dynamics in order to put even more secure constraints on the IMF slope and in general to study the structure and evolution eventually of very massive galaxies. And then finally I'll spend some minutes on the future work I'm planning to do, and who knows, maybe here in Tenerife with the Marie Curie Fellowship. So let me start from the XLENS survey, and in particular, let me introduce to you the goals and strategy of the survey. What do? We spectroscopically observe a sample relatively small for the moment, 10 galaxies, of very massive early type galaxies, the red and dead galaxy usually you can call, and they all have velocity dispersion above 250 kilometers per second, and they range in redshift is between 0.1 and 0.4, although we have two very massive galaxies with redshift higher than 0.5, 0.6 and 1, that is ongoing analysis, and we hope to publish them soon. And as I told you already, we're using strong gravitational lensing, so those are lenses that produce multiple images of a quasar, of a star-forming object far behind, and we use the deviation in order to infer the total mass of the object. Then we have specially resolved kinematics that is performed by X-shooter high signal-to-noise spectra. And finally, we have, on the same spectra, we perform stellar population analysis using simple stellar population modeling, line index, and eventually full spectral fitting in some cases. So this is the current sample. The black points here are the 10 galaxies I have analyzed and published in Spiniello et al. 2015C, which is the survey paper, I'm sorry. And here you can see the velocity, the parameter space in velocity dispersion and redshift. And those boxes here show different samples, for instance, the Corroy and Van Dokkum sample, the Spider sample by La Barbera et al., even the SDSS subsample that I've used, the massive sample, and those are the most, the Atlas 3D, I was forgetting the most important one, and those are the most well-known and well-used sample to study stellar population and kinematics in the ETG constants. And as you can see, we're extending the velocity dispersion range, and above all, we're going further away in redshift. And we can do that just because, or just thanks to the gravitational lensing, to the strong lensing that provides you a very easy and very precise constraint on the total stellar mass, and in some cases, thanks to the cauldron analysis that I will introduce to you in a while, it allows you to put constraint on the baryon content, on the stellar mass of this system. This is just an example. It's a spectrum only in the UVB and optical part, because the near infrared is still work in progress. And here you see a galaxy with 0.2, with redshifts of 0.2, and the integrated signal to noise for this particular object is under 20. So as you can see, those are very, very good spectra. And this is an example of another galaxy. I don't remember the redshift, but it should be 0.15, for which we're performing the kinematics analysis by using the PPXF code by Capellari and Emseller. And this is the residual, and the black line is the galaxy, whereas the green line is a combination of stellar templates that have been used to constrain the velocity dispersion. And this is one of the least massive, if not the least massive, of the sample. Then, again, using X-shooter spectra, we split up the spectra in different, different distance from the radius, and we perform spatially resolved kinematics, and we go always up to 0.7, but most of the time up to 1 or 1.5 effective radius. And we calculate rotation velocity and velocity dispersion. You can see that in some cases we have hints for rotation. In some other cases we have flat profiles. And the velocity dispersion are either flat or showing the typical shape of having a maximum in the center and then declining. So we have, we're analyzing a representative sample of the red and dead galaxies that are often analyzed with lambda spatial profile, and that have been studied by Atlas 3D in order to show that there's a dichotomy between fast rotator and slow rotator. So this lambda parameter is nothing else than the angular momentum of the galaxy. It shows the angular momentum of the galaxies, and here we're tracing the lambda spatial profile for the 10 galaxies, and here we're plotting the lambda epsilon relation in order to get the distinction between fast and slow rotator. And I'm not sure you're familiar with Atlas 3D results, but Capellari and his team, they find that the formation scenario for those two different families is different. So fast rotator and slow rotator are two almost completely different family of galaxies, and their kinematics and their structure is different. And for instance, work I'm carrying on with different people in Naples and in Groningen consists of studying the H3 and H4 Gauss-Hermite parameter for those galaxies with integral phase spectroscopy, for example, a galaxy with integral phase spectroscopy. And it can be shown that in case of slow rotator, in case of different families, you have completely different shape for the higher moment of the velocity dispersion. So, studying the kinematics and eventually adding stellar population analysis is a good way, is the best way so far to understand the formation of different kind of system. I'm not going into too much detail because I want to spend most of the talk talking about IMF, but if you have questions, I'll be happy to answer. So this is everything is presented in this paper, 2015C, and the dark matter side of the story is still missed, and it will be presented in a paper, in an upcoming paper. We hope to publish it this year, but I would say 2016 to be honest. And the dark matter fraction are computed by using the cauldron code. I'll explain you later. But basically, by using lensing and dynamics, and additionally extended stellar kinematics, we can get the fraction of dark matter within the effective radius. And we find two things. We find that we have higher fraction of dark matter in lower density, in system with lower stellar density, and with system with higher velocity dispersion. That means more massive system. And this is in agreement with previous studies, for instance, Capellari et al. And the Atlas 3D paper, Auger et al. Based on gravitational lensing again, and Sonnenfeld et al. Based on gravitational lensing plus dynamics. So again, we find higher fraction of dark matter in more massive systems and in less denser system. From the halo shape point of view, we find that dark matter and star shape are similar, although the dark matter halo are usually slightly rounder than the stellar component. They lie on top of this line. But to be honest, the errors are quite big, and we don't have secure constraint on the halo shape. So I will not draw too many conclusions on that. Now, why are we doing this? As I said, we want to understand the evolution and internal structure of massive early type galaxies, and in particular, we want to kind of test the hierarchical galaxy formation scenario, and in order to do that, we really have to well understand the relationship that exists between baryonic and non-baryonic matter. As you know, baryonic matter is concentrated towards the central part of the galaxies, but for these massive galaxies, already at the one effective radius, the dark matter component play a non-negligible role, ranging between 10 and 40% of the total mass budget. So it's really important to understand what's the relation between dark matter and non-dark matter in the internal structure of this system. And therefore, it's really important to be able to properly disentangle the luminous from dark matter. How do we do that? We use a strong gravitational lensing and stellar kinematics in order to have a very precise one-shot estimation, only dependent on gravity, of the total mass, within an aperture, obviously. And then we add stellar population analysis that obviously will give us the stellar mass. The good thing is that using the combination of these three or two technique, if you want, we can disentangle the luminous from dark matter, but the bad thing is that we need a lot of very good data. From the strong gravitational lensing point of view, we need HST, because we need high spatial resolution, and we need to solve the mass shift degeneracy, and we really have to correctly analyze the system. From the stellar population analysis point of view, we have to pay a lot of attention on the IMF, because it's crucial to determine the mass to light ratio, and in order to do that, we need high signal to noise spectra, and obviously good simple stellar population models. The important thing is that we do it completely blindly. So Matteo Barnabé at Dark Cosmology Center takes care of all the strong lensing aspect and stellar dynamics analysis, and we do not talk. I take care of the other part, the stellar population analysis part, and we do not talk until we reach results, and then we compare the results. In this way, we can check for systematics of the two single techniques, and we can be sure that we're not biased one with the other. You know, Matteo's not getting the result I'm asking him to get, and vice versa. So I told you that it's really important for us to break the stellar versus dark matter degeneracies. But a big question here is dark matter in massive early type galaxies really dark, meaning non-baryonic, or it's something we cannot see in the light, so from the spectra? In other terms, do massive early type galaxies have more internal non-baryonic matter, as I showed you before in the plot? This is just a sketch that shows the same result. Or do more massive ETG have a different initial mass function normalization, meaning more stars with masses below 0.5, 0.3, low mass stars, as it has been claimed by Van Dokkum and Corroy in a Nature paper in 2010, and then confirmed by several authors like La Barbera, Vatstekis group, and also myself. Can we disentangle between the two scenarios? In order to do that, obviously, we have to put a completely independent constraint on the low mass stars amount. We have to constrain the dwarf to giant ratio. In other terms, we have to be able to infer the low mass end of the initial mass function in early type galaxies by looking at the spectra, their spectra. So just to be sure that we are on the same line here, what's the initial mass function? The initial mass function is the number of stars that have been formed in a single burst of star formation, okay? And usually you define it a la Salpeter, so with the power law, and here I'm only showing what we call unimodal IMF, but this is not the only possibility we have. We can have a la Krupa, so the one that is measured in the Milky Way actually, which is a tapered power law, it's a broken power law. And another thing to pay attention to is that we are only talking about the low mass end of the initial mass function. That means that we're stopping at roughly 1.5 solar masses, because we are dealing with very old stellar population systems, and in this kind of population, everything above 1.5 solar masses is already dead by now. So we can put constraint only in this part of the IMF. And here I'm showing different IMF. I will refer to a Milky Way-like because it gives me, although it's unimodal, it gives me the same mass to light ratio that I will have if I use a Krupa or Chabrier-like IMF, Salpeter-like IMF with an exponent of 2.35, and I will refer to those ones as bottom-heavier IMF, because I'm increasing the number of low mass star. And the cutoff mass is basically this lower, the lower limit of the integral I'm using to compute the stellar mass. Why is this important? Because different stars start with different masses are contributed differently to the light and to the mass. In particular, low mass stars, dwarf stars, are critical for the stellar mass to light ratio, because they contribute up to 60% in the optical to the mass, but they only add few percent to the optical light. So by changing the low mass end of the initial mass function, you are dramatically increasing, by making the initial mass function bottom heavier, you will dramatically increase the mass to light ratio. I have to be precise here, this is only true for this dramatical increase is only true in the case of unimodal IMF. It gets more conservative in the case of bimodal IMF, and that's why I'm looking forward to collaborate with Alejandro Vazdeikis, because his models have the possibility to change the IMF in the way we need to. So how can we constrain the IMF slope directly from galaxy spectra? Basically by looking for features, absorption features, stellar absorption features that are there only for those particular cold and dwarf stars. So this is an example. This was in the original Nature paper by Conroy and Van Dokkum. Here you can see the sodium line, the sodium doublet, roughly 8,000 angstrom, and here a wing-4 molecular iron band. And as you can see, you have 3 different kinds of stars, and you only see the features for the M dwarf. So if we find those kind of features in the spectra of a galaxy, we can basically almost count the number of dwarf stars. Why almost? Because we have to deal with degeneracies, like age metallicity degeneracies, IMF metallicity degeneracies, temperature, and there are so many parameters. But this is the main idea. You find the features that is there only in case of dwarf stars, and you study their behavior. For instance, those are 2 optical features. You study their behavior in simple stellar population model. Here I'm using Conroy and Van Dokkum models, were the ones used in the Nature paper, and they allows me to change the age and the alpha to iron, but they do not deal with total metallicity. Here different colors are different simple stellar population model with different age, and different samples are modeled with different alpha to iron. And as you can see, if you take the Krupa-like or Milky Way-like IMF, for this particular feature, you have, it goes down, the equivalent width of this feature goes down with age, with increasing age, and goes up with increasing alpha to iron. And in this case, it's almost insensitive to age, especially for, let's say, 9 and above, so between the green and the orange, and it goes down if you're changing the alpha to iron. And both features are going, both equivalent width are going up if you're changing the IMF. Okay, so this will be something that I can call IMF-sensitive features, because the more the IMF is bottom heavy, the higher the equivalent width you will measure is, the stronger this line would be. Okay, the higher the contribution of the dwarf is, the higher the stronger this line. And this is a collection of lines I have found, kind of, or I've used in 2013 to study the IMF of very massive galaxies. And here you can see some of the lines that are completely not dependent on the IMF. They are flat, they are not changing. And the ones I've shown you before, TIO2, KH1, that are increasing with increasing of the IMF, most of them are coming from TIO molecular line, as you can see. Then there are some that are alpha to iron dependent, and there are some that are almost independent on alpha to iron. So basically, if you use an ad hoc combination of several of those lines, you can get rid of the degeneracies, and you can measure the IMF, the alpha to iron, eventually the metallicity if the model allows you to do that, and the IMF slope. That's exactly what we did. We use a very, very simple approach. We measure several indices. We compare each we measure them in the galaxy and in the simple stellar population model, and we compare each galaxy spectrum with grids of SPSS model, making the grid as wider as possible. And in order to do that, this particular work is based on SDSS galaxies that are stacked in 5 velocity dispersion bins. I will show you in a second the results, but basically we compute a probability density function via the likelihood function, and it's a chi-square basically, and we find for each beam, for each velocity dispersion beam, we find the best fit parameters. So we find the best fit age, we find the best fit alpha to iron, the best fit IMF, and this is the temperature of the RGB, because making the RGB colder could mimic a bottom-heavy IMF. So in theory, this is a parameter we should take into account. And this is the main result. Here I'm plotting the velocity dispersion, so those are the 5 points I was referring to. Those are stacked sample of SDSS galaxies. Mainly for each point you have 50 galaxies that have been selected to have 20 kilometers per second of difference. You can read it here in log. And here I'm plotting the ratio, what we call the mismatch parameter. That's the ratio that you will get, the mass to light ratio that you will get by using the inferred IMF, so the best fit IMF from the models, from the chi-square analysis, divided by the mass to light ratio you will have by using a standard salpeter IMF. Okay, so this number will be higher if your real IMF, it's a bottom heavier IMF, and will be smaller if your real IMF, the inferred IMF, we're always modeling, will be less bottom heavy than salpeter, so Chabrier-like, it will be tapered, okay? So this point over here are all the galaxies analyzed by Atlas 3D people, and obviously there's nothing including simple stellar population here. This is just dynamical based result. But the other lines, this is a collection of other people's work. They did exactly what I just described to you, using same model but different system, or different models and different systems. This is, for instance, based on La Barbera et al. 2013, made using the SPIDER survey and using the SSP models by Vazdekis and al. 2011, right? And then finally, the blue line here, it's something based on strong gravitational lensing plus dynamics analysis. This is not as good as the analysis we perform, but it's still based on the possibility to use gravitational lensing to perform the total mass and eventually to get the stellar mass. Okay, and as you can see, you have a beautiful agreement in this mass range. So for massive galaxies, starting from 220 kilometers per second, 250, no, I'm sorry, this is much lower. This is 150 kilometers per second, going up to roughly 400 kilometers per second dispersion. You have a non-universal low mass end of the IMF. There's evidence for a steepening of the low mass end of the initial mass function slope with increasing velocity dispersion. Okay? This was where we stand in 2014, roughly. Now, before I move on, I told you that there was another important parameter together with the slope that was crucial to calculate the mass to light ratio, and this parameter is the cutoff mass, so the lowest limit of the integral you're computing. The cutoff mass is something that you can never constrain by looking at light, because this is the cumulative luminosity of stars per unit of star of different mass. And if you look, the theoretical cutoff limit is 0.08, the hydrogen Bernoulli limit, so will be roughly here. And those 4 lines are 4 different IMF, from Chabrier to 3.5, so an extremely bottom-heavy IMF, and as you can see, they do not give any contribution to the light, whereas they give a very different and substantial contribution to the integrated mass. So by changing the cutoff between 0.08 and 0.1, you will change the mass to light ratio by at least a factor of 3. And this, well, I can show you again, this is the cutoff, and this is until now a fully unconstrained parameter, despite being critical for the stellar mass to light ratio. And the thing that is really driving me crazy is that different codes, different stellar population codes, are actually using different assumptions for this number. Some of them are using the hydrogen Bernoulli limit, 0.08, some other are using 0.1, 0.92, 0.092, 0.115 is the one used by Bourgeois and Charlotte 2003. So, you know, if you're not aware of this situation, you can have very different mass to light ratio, and you can you know, you have trouble understanding what's going on. So this is a very important, I'm not claiming I know the answer. I'm not claiming that I know that this is universal or not universal and which one is the good one. I'm just saying that we have to pay attention to the assumptions we're making when we're performing such a study. And again, as I said, it's impossible to get the lower mass limit by looking at light. That's why we need something else. We still have the spectroscopic simple stellar population analysis, exactly in the same way I just showed you, and we trace the light, but we add a joint self-consistent lensing and dynamic analysis that is actually tracing the light. Sorry, it's actually tracing the mass, so it measures everything is there. Okay, by comparing those two independent constraints on the stellar mass, then eventually we could have some constraint or some ideas of what's going on with the IMF slope and the IMF cutoff. So this is what I just described to you. It's exactly the same. The big assumption here, the simple stellar population method, the big assumption here is that all the stars were born during a single star formation burst. I'm using a simple stellar population model to get my IMF measurements. So this is a very big assumption, and we kind of know that this assumption is wrong. Then I'm using line index measurements, so equivalent width. This is basically the number I get is the area within this value, and this is the continuum, the blue continuum, the red continuum using to normalize the number. And I'm using two different simple stellar population models that I am extending and combining together in order to get a full covered parameter space. In particular, Corroy and Van Dokkum models, they do deal with alpha to iron, but they don't allow you to change the total metallicity, whereas the MuSCAT is exactly the other way around. So I'm using response functions and derived from one and apply to the other, derived from this and apply to the one to get a total coverage of the parameter space and be able to change age, metallicity, alpha to iron, again, temperature, as I said, and initial mass function slope. The huge limitation of this method is that I have to use the unimodal initial mass function slope because it's the only one that Corroy and Van Dokkum have. So if I want to combine the model, I have to use the unimodal. But the situation is changing because Alejandro is providing community with a MuSCAT version that allows you to change also the alpha to iron. So in the future, we will have one set of model able to explore the full parameter space for massive early type galaxies. And this is the lensing model made by with the use of Cauldron, which is the combined algorithm for unified lensing and dynamics reconstruction. And here we have a lensing model that is based on pixelated source reconstruction method, and it's performed on HST images. As I said, we have multi-band HST images for those 10 galaxies and for many more galaxies. It's the SLACS sample by Bolton et al. And we're planning to extend them in redshift and in mass and perform the same analysis. We already started, but it's expensive in terms of time and resource. Then we have, obviously, we need some mass modeling and dynamical modeling. For the dark matter halo, we use an axisymmetric generalized Navarro-Franken-White density profile, as you can see. And there are so many free parameters in the models, but we can deal with them, and the model is really, really robust. And for the luminous mass distribution, basically, this allows you to get the total mass, but we want to have also the stellar mass, and that's the real novelty of this method that was presented in Barnabetto 2007 and then uploaded in Barnabetto 2012. So for the luminous mass distribution, we use a multi-Gaussian expansion (MGA) technique to get the from the surface Brighton profile to get the luminous mass. And so basically the luminous mass distribution is self-gravitating, it's just not just a tracer. And obviously the free parameter is the baryonic mass in the model. Well, the method was developed by Emseller Capellari. It has been tested, and others 3D people are using the same model. And finally, we use anisotropic gene sequestration, Capellari et al. 2008, and anisotropy is taken into account in the model. So with this model, we can have an estimation, a measurement of the baryonic mass, as well as a lot of parameters about dark matter halo and concentration, velocity, axis radius, and so on and so forth. And again, the information about the dark matter constraints and the dark side of this project is made by Matteo Barnabe at DARC in Copenhagen, and 2 papers are on their way. This is already published in a letter, Barnabe Spiniello et al. 2013, if I'm not wrong. And that's indeed an example of lensing plus dynamics, PDF, 2D PDF, probability density functions, and inferences. And here I want you to focus on the baryonic mass, because this is the quantity we're going to use with the stellar population analysis to combine them and to get the IMF. And here for this particular galaxies, which is one of the most massive with a velocity dispersion of 330 kilometers per second, we get 10 to the 12 solar masses. Then, exactly in the way I just described, by comparing simple stellar population model line indexes with galaxy line index, we got the best fit estimation, the best fit age, the best fit alpha to iron, and the best fit IMF slope. And using isochrons and using the Dartmouth code, we can get for those parameters, and by assuming different cutoff mass, we can get different mass to light ratio. Knowing the luminosity, we get different mass, okay? So for instance, this is the mass we get when we assume 0.115, which is the maximum possible values used by common codes, Brusois and Charlotte, 2003. And this is what we get when we're assuming 0.08, which is the hydrogen Barlin limit, and it's the lowest one used by Corroy and Van Dokkum. So basically, we are computing the integral, stopping in different places. So here I'm stopping at 0.115, and here I'm stopping at 0.08. And I get different masses because, as I said, these guys, these very low stars, are not contributing to the light. They're not changing the luminosity at all, but they are dramatically important for the mass. So this is what we get from stellar population models, the colored line, and here the purple one is the one that assume 0.08, and the green one is the one that assume 0.115. The curve here, the histogram here, shows the right IMF. So the IMF that we infer is 2.6, and dispersion and the error is 0.3. Okay? Here I'm also plotting what it will be with a different IMF. So if you assume an 0.115, and instead of having a 2.6, you use a salpeter IMF, you will be picked here. If you use a Chabrier IMF, Chabrier-like, it's all unimodal, you will be picking here. And the same for the purple line, okay? The black histogram is instead what we get from lensing and dynamics, so the baryonic mass of 10 to the 12 solar masses. As you can see, for these particular galaxies, assuming these stellar population parameters and these 2 cutoff mass, we are overestimating the stellar mass. So we have more than 100% in star, because as I said, this is everything. This is our maximum limits. We cannot have more than that. So the upper limit to the IMF slope for this particular galaxy will be slightly above salpeter for this cutoff mass and slightly below salpeter for this cutoff mass. Obviously, we can play with the cutoff mass as much as we want, because we have no constraint from the simple stellar population, from the stellar population analysis point of view, and we can move it as much as we want until we reach the perfect agreement. This is nothing scientific, it's just playing with number and see where we find the agreement. So for this galaxy, if we believe that our inference on the IMF slope is correct, and we do believe because we have been testing it and, I did the measurement, so I have to believe my own work. If we believe that the IMF slope we measure is good, in order to have an agreement between the stellar mass we measure with lensing and dynamics and the stellar mass we measure with this simple stellar population method, the cutoff mass has to be 0.15. Okay? So in other terms, what I'm telling you is that there's a degeneracy between the IMF slope and the cutoff mass. We don't know whether. We know that both of them cannot be universal, because we have plenty of line of evidence that show us that we cannot trace all the galaxies with the IMF that looks like the one in the Milky Way and with the cutoff mass that is equal for all of them. So either we play with the cutoff or we play with the IMF slope, but one of them have to change. Okay? And this is, for instance, when we use MCMC Markov chain Monte Carlo to sample the joint lensing, dynamics, and simple stellar population posteriors on 9 of the 10 systems. For one of them, we're missing the HST data. So it's just starting noise. So we decided to throw it away, and we varied the IMF slope, the cutoff mass, and the luminosity of the system at the same time. We get this banana shape that shows you the degeneracy between them. And for a representative system with a velocity dispersion of 250 kilometers per second and the effective radius of 10 kiloparsec, we get that the IMF slopes are, this is beta, it should be x. We changed the notation on fly. This is the same exponent I was showing you before. It's slightly higher, but still consistent with salpeter IMF. There's no way that massive galaxies can match a Milky Way like IMF at the low mass center. And this is 250 kilometers per second, which is the lowest velocity dispersion we analyzes. Okay? And then the cutoff mass, as I said already, it's higher, but still consistent with some of the ones that different codes are using. And this has been published in Spiniello 2015. Okay, let's go back to the evidence that we got for a steepening of the low mass end of the IMF with mass or velocity dispersion, okay? This was the first results, and we were kind of happy because we thought we knew what was the parameter driving IMF variation. We thought we knew that the more massive the galaxy was, the more the IMF or the mismatch parameter was changing with respect with Chabrier-like. So more massive galaxies have a bottom-heavy IMF. And as I showed you, different groups with completely different and independent methods, they were reaching the same conclusion. So 2 years ago, we were confident that we kind of knew the answer. And then came Smith. Russell Smith published a paper in 2015 and the previous one in 2014, showing that there were few galaxies, lenses galaxies, they were very, very massive. They were having a very high velocity dispersion, above 300 kilometers per second, and they were not respecting this IMF velocity dispersion law. They were consistent, they were having an IMF which was consistent with the Krupa Milky Way-like IMF. And, you know, it was comparing dynamical results with IMF, with simple stellar population-based results. And the claim was that perhaps we were, from the stellar population point of view, we were not counting low mass stars, we were tracing something different, or probably we were not able to break the genesis between metallicity and age. So, you know, there's a velocity dispersion metallicity relation. So maybe we thought that was velocity dispersion driving the IMF variation, but instead it could be metallicity. So the situation is still highly debated and very, very complex. So maybe with our MCMC method, with gravitational lensing plus dynamics plus stellar population, we can help here, because we have a way to correlate the IMF with galaxies' properties. And it's a self-consistent way, because it's totally based on Bayesian statistic, and, you know, everything is taken into account from prior to posterior point of view in a consistent way. And those are a very complicated plot that takes me forever to understand, but what you should focus on is this here, again, is the IMF slope, the variation of the IMF slope with sigma, and that's the 1D integrated plot. And here you see the variation of the cutoff mass with sigma. And when we do it in a consistent way, changing at the same time and low IMF slope, luminosity, and tracing the stellar population analysis as well as the lensing analysis, we do not get any correlation between the IMF properties and velocity dispersion. Okay? So as soon as you allow both of them to change, then you don't see the correlation anymore. And again, we did some tests, and we thought it could be effective radius, or, you know, some sort of a concentration parameter. So we try to change to study the variation of the IMF slope with effective radius and the cutoff mass with effective radius. And indeed, we find a slightly significant direct correlation, in the sense that bigger galaxies have a bottom heavier IMF. And then we also added the 3 galaxies from Smith et al. 2015, where we were having exactly the same set of data, because those are massive lens galaxies, so we could easily plug those 3 galaxies into our code, and basically the situation doesn't change at all. You see a flat IMF versus sigma, a roughly flat IMF versus cutoff mass variation, and you still see, so basically the way you have to look at, if this parameter is non-zero, then you have a variation. If it's 0, peaked around 0, then it means that you have no variation, then it means that there's no correlation between them. And we find the same conclusion, just with smaller error bars. So no correlation of the IMF slope with sigma, when slope and cutoff are varying at the same time, and slightly significant direct correlation between IMF and size. Then we thought, okay, what's going on here physically? What are we really observing? What are the evidences we have and we didn't consider yet? And as I show you 20 minutes ago by now, there was evidence from Sonnenfeld et al. 2014 that the density would play a role in the non-visible matter. So actually density is nothing else than a combination of sigma and effective radius. So we tried, maybe just for fun, to combine those 2 quantities, and we defined the total density of a system as sigma square over effective radius square, and those are the results. Here you have the slope, here you have the cutoff mass, and they agree with the previously obtained results. Here I think it's 2.37. the best fit, whereas it was 2.41, so well within the error. This is including also the 3 Russell-Smith galaxies. And here you have the cutoff mass, which is roughly in agreement with the previous one. And here you have variation of the IMF with sigma, with density, and variation of the cutoff mass with density. And here you have something that is, you know, significant at 1 sigma level. It's still really, really poor constraint, but this is the first explanation. I'm not sure it's the right one, but we are making progresses. And because I need to visualize things very, very easy and simply, I made this plot myself, just taking the IMF slope I got from the simple stellar population analysis and plotting it versus the total density. Black galaxies are the XLENS galaxies, red galaxies are the Smith et al. 2015 galaxies, and as you can see, it looks like there's a sort of an agreement here. So the highest the density is, the less you need to change the IMF slope. Okay? So the very, very high density system, the Smith et al. System, is totally consistent. I understand that the error bar are big, but you know, take it as a general idea. It's totally consistent within the error with a Milky Way-like IMF, slightly steeper perhaps, but totally consistent with what people call a universal IMF, whereas this guy here that has 2 or even 3 order of magnitude, that is 2 or even 3 order of magnitude less dense than this guy here, requires an IMF which is bottom heavier, and it's inconsistent within 1 sigma with the Salpeter IMF and within 2 sigma with the Milky Way IMF. So my conclusion is I will really, really be surprised if we have to go back to a universal IMF. I believe that the low mass end of the initial mass function slope is not universal, but I also believe that we are not completely done with what's the driver behind IMF variation, why we're observing variation in the IMF. And I have to mention Nacho, Martin Navarro, because he has done a lot of work in this context, and I believe that total metallicity plays an important role here, and it looks like higher systems with larger metallicity do require a different IMF. And coming back to the formation of these systems, I think it has to do with the way the clouds collapse and fragment. So we have, in theory, to understand the theory, well, this is my conclusion in the meantime. To understand the theory of IMF variation, we really have to pay attention to talk to theoreticians and to understand what is what's going on when a galaxy forms from the point of view of density, from the point of view of fragmentation, from the point of view of velocity of the formation. Because as you know, alpha to iron, or maybe you don't, I just learned it, alpha to iron trace the speed of the formation, how starbursty was the process. So higher alpha to iron means quicker star formation event, starbursty star formation event. So these can be also an important factor. Maybe galaxies that have been formed in a starbursty environment, they could have fragmented more and so form more dwarf stars, or maybe metallicity plays a role because, you know, metallicity is driving the high mass end of the IMF, so maybe it has a it gives a contribution to the low mass end as well. Obviously, velocity dispersion does play a role, but we don't really mass, if you want, does play a role because we only observe variation in systems that are more, that have velocity dispersion above 150 kilometers per second. Everything else is consistent with the Milky Way IMF. Again, the low mass end of the initial mass function slope cannot be universal. Now we have to put effort, we have to combine our efforts, theoreticians and observers, in order to understand why and how in theory. And we have to build a comprehensive scenario that is able to match the high part of the mass of the initial mass function, because this is necessary to constrain the chemical evolution of the universe, and the low mass end of the IMF, because this is necessary and crucial to understand mass to light ratio and therefore galaxy formation. Those are my conclusions. I've shown you that the combination of lensing, dynamics, and stellar population analysis is a very useful technique and very useful tool to study formation and evolution of galaxies, of massive galaxies. Evolution, why? Because the lensing method is the only one that allows you to go to redshift above, say above the local universe, above 0.01, 0.02. And we are able to break the dark luminous matter degeneracies, and we also find that higher fraction of dark matter, or invisible matter if you want, are found in systems with lower stellar mass density and with higher mass. And then we're able to constrain the slope and cutoff mass of the stellar initial mass function by combining, by adding also the stellar population analysis information. And we find for a system of 250 kilometers per second and 10 kpc as effective radius, we find something that we find a slope that is consistent with salpeter and a cutoff mass that is higher than the hydrogen Barlin limit, still consistent within the error with the one that has been used in Bruce-Charlotte, in Pazdekis models, stellar population models. And then we actually don't know yet what's the main driver behind IMF variation, and more investigation is required. And my way to do that is looking for gradients in the IMF normalization, as Nacho is already doing. So I believe that the formation of very massive galaxies has to do with mergers, and it occurs in a starbursty, in a more starbursty environment. I believe those galaxies are the end product of merger of different systems with smaller mass, and if merger and accretion plays a role, then probably we should see the bulk of the population that has been formed early on in the universe could have a different IMF, because condition, density, Mach numbers, basically, if you're a theoretician, and density, temperature of the cloud, of the gas cloud, were different. And then those smaller system guys that are accreting, they were formed later on, so they could have a more standard universal IMF. If this is true, then you will observe gradients, in the sense that you will have the central bulk of the population having a bottom-heavy IMF, and you will have something declining and getting more universal towards the effective radius, for instance. This is exactly what Nacho has showed in his paper, in his plenty of papers in 2015, and this is exactly what we observed with Muse data in collaboration with Mark Sarsi for M87. We observed that the IMF seems to be extremely bottom heavy in the innermost region, and then it declines and goes up to a Krupa-like IMF at one effective radius. So more job is required, and I think the best way to go is integral phase spectroscopy. In particular, I'm planning to use MANGA, which has a wide enough wavelength coverage. I need the blue part of the spectrum to constrain the age and to constrain the metallicity, because that part of the spectrum is completely independent, or almost completely independent on IMF, but I also need the red part of the optical and eventually the infrared, if I can have it, because there the contribution coming from M dwarf is higher, and so I can really count low mass star. So bottom line, the more we get, the better it is, but I also need extremely good spatial coverage, and I think I need infrared integral field spectroscopy, because in this way I can produce 2D map. I can really, you know, for instance, I can trace the accretion of systems. I can really understand the spatial structure of IMF, age of the stellar population contents of these galaxies. Again, because the infrared plays an important role here, I have been starting a project with Lodovico Coccato at ISO. He's taking care of my X-shooter spectra, and eventually we're asking for more time. The infrared is tricky because you have a huge contribution from telluric lines and sky problems, so it really requires a proper data reduction and analysis, and you know, telluric correction is really hard, but we are confident with a super high signal to noise spectra, super high signal to noise ratio of our spectra, we can find many new IMF indicators in the infrared, and combining them with the optical indicator will put new and more secure constraints on the IMF slope and cutoff mass. Final goal is to constrain the IMF per unit of mass. So different features, for instance, sodium is different from iron, is different from thiol. Different features are coming from stars with different mass. The sodium wing-fold band here, it comes from stars that are extremely low in mass. Above 0.2, it doesn't contribute at all. Sodium, which is not even listed here because I have some trouble with sodium, sodium comes from stars between 0.3 and 0.5 solar masses. And then you have thiol that is very, very strong in giant stars and dwarf stars of any mass. So by combining different elemental abundances, you can really count the IMF in unit of mass. And that's my final goal, and this is also the main topic of my application for a postdoc. And I think I can finish here and leave plenty of time for questions. Thank you. I can try to repeat the question through the microphone. Thanks. So the importance of the assumption of the simple stellar population model. You're completely right. The assumption is a big assumption, and it might be wrong. I have to say that it's wronger for smaller systems. So smaller systems show a variety. No, you're right. It's wrong also for massive ones, but it's wrong for all the galaxies, but the situation is even more complicated for smaller systems. But my answer to your question is the following. We perform a toy model in which we do not really use we don't really trace the star formation history of the galaxy, but instead of using only one simple stellar population model, we use plenty. So we allow for different starbursts, okay? And if we do that, and we repeat again the whole, and basically I'm taking a spectrum of a simple stellar population that has been formed 13 giga-years ago. Then I'm summing it by mass with a spectrum of, I don't know, 3 giga-years ago, simulating a second starburst in time, and then eventually I can add a different metallicity, a spectrum that has been formed, a simple stellar population model that has been formed with different metallicity, and I'm trying to see whether I can match all the galaxies, all the points within a galaxy with a single IMF. And the answer is no. I still need to change the IMF. Situation becomes much more complicated, and that's why I didn't publish the paper yet, because you have so many parameters to explore, but the answer is the IMF still needs to change. And it needs to change in the same, towards the same direction. You still require at least the bulk of the, at least one of the starbursts that I apply to my very massive galaxies have to have a bottom-heavy IMF. Mm-hmm. I completely agree. I think in order to solve this question, we have to go to full spectral fitting and full extended star formation. We have to take into account the spread. And yeah, we're already working in this direction with a colleague of mine, Simona Vegetti, you know her. Simona is, we are writing together a code that will take into account the full star formation history of a galaxy, and she will also, she's a super mega expert in Bayesian analysis, and so she's performing a hierarchical Bayesian code in order to put at the same time everything together. So she wants to explore the correlations with galaxy parameters. She wants to trace the full extended star formation history, and she wants to correct for this IMF age metallicity degeneracy. And that's the reason why we need full spectral fitting. You have much more information, whereas with indices you are losing. But this is a full talk, it will take me an hour to explain. I can show you more stuff, but not now. Mm-hmm. Mm-hmm. Yeah, but no. So the question concerned the hot corona that is surrounding the galaxy, and well, the point is that this could contribute to the invisible matter. And yes, you're right. The only answer I can give you is that I think that spatially we're not going further enough. We're not going far enough. We are restricting ourselves to one effective radius, so I don't think the contribution of the hot corona is so high. Okay, so oh, you're right. Okay, I'll ask Matteo and I'll let you know, but I think there is a contribution. I think part of the invisible mass could definitely come from a hot corona, but I didn't think it was so important because I thought it was more externally located.
Two comments. One for Chiara, and they will start with the more extended.
Should I repeat again? Do you want to have the microphone so that?
I think it's okay. So, I mean, this is about the extended star formation history remains the contribution of the IMF. If you remember, we talked about the magnesium over iron issue, at the very beginning, back in the
Agree.
89, I have to say, it's Vernier the first person who pointed this out.
But nobody believed him.
It was Vernier here in his testimony, never published to say that. And this has been acknowledged by the way by Walter, okay?
Uh-huh.
Not just my because he's my friend. Okay, so the question is that at that time, that was the same argument, whether more extended star formation is good. So, and the answer was as simple as that. I mean, you cannot build a magnesium enhanced population, okay, with the solar,
Abundance.
Because, and for the IMF, for example, is the same story. for example, put as an example one of and solamente. Exactly. It's not the level of the giant ellipticals we're talking about. It is very near.
Yeah, but not as much as giant elliptical. Giant elliptical are much more richer.
That's the point. I mean, you are building your models on the basis of solar neighborhoods, sort of stars of intensity, and there is no way. You have to vary the output ratio of the two. I mean, in fact, it's computing what you're saying. And you need to have the stars that are pronounced. I will put just one example with the tire. I mean, it's one of Chiara's favorites. Okay? The tire 2, for example, has such a high value in the giant
Yeah.
that whatever you do, whatever combination of operations you mix, will never get as high if you do not try.
I don't have the plot with me. Oh, yeah.
Because you no way, by writing whatever you want, you never can reach such high titanium oxide, for example, or the other values, or for example, having such high titanium oxide values and such low calcium values at the same time. Okay?
Yeah, can I add something? If you only have one, yeah, really, really short. If you have only one indicator, this is a game you can play. You can say, okay, no, it's not IMF, it's an extremely super high titanium over iron abundance. So you have an extremely weird population. But then you have to match the other 10 indicators you have, and if you have an extremely high titanium over iron abundance, you don't match the calcium, or you don't match the sodium. That's why I'm always say people that they should use as many indicators as they can, because they have to be able to break the generacies. And the only way to reconcile everything is to change the IMF. There's no other way.
Okay,
Well, together way.
Okay, so now just about this lower mass cutoff.
Yeah.
The only this is as a comment, okay, just for you, is that particular change in the lower mass cutoff is something that is an issue, okay, with the unimodal line.
Yeah,
or,
completely agree.
It is not an issue if you use sort of generalization of the what we call the bimodal or any kind of IMF like that.
That's the reason why I want to work here.
And then the question is, big galaxies, I mean massive, like, you know, this like the one that we published about the relic.
Yeah, that's don't ask me that question. It doesn't fit. I haven't tried to put the galaxy on that plot yet, and this is something we're going to do this week with Nacho, but it doesn't fit. Because there you have a very bottom high IMF, and actually you do not have any gradients or anything, so radius doesn't play a role at all, and they are super dense. So, yeah, the answer is I don't know. It's the metallicity there. Yeah, I agree. No, I completely agree, and yeah, and that's why I'm really looking forward to play the same game by allowing the IMF to break in several pieces. And I think situation is not going to be that dramatic in that case.
One more question. Okay, so this is not really scientific, it's more technical, but slightly scientific.
Go ahead.
So
Should I be scared? That's again another whole talk. Yeah. I think you should answer to this question. I mean, yeah, Alex. It's okay.
Well, there's a,
Yeah.
there's a recent paper by John Vandenberg about that, saying that magnesium over iron as an impact. But it's always, and this is very important from Vandenberg work, it is the metallicity that may probably changing the giant particle. But still you can have second order, let's say, correction with maybe it's around 50 Kelvin. I mean,
Between 50 and 100.
Change means like 200 Kelvin difference in the very giant particle. Okay? Changing the magnesium over iron will influence as much as before, maybe 250, but no more. Okay? And that's the
Practically what Charlie Conroy is the author of this part of the thing, and practically what he does is it changes the temperature. He uses colder stars, colder isotopes, without changing anything else, and he assumes that he can do that. So that you know, it's not degenerative, but we know that there is degeneracy. Keeping it short, keeping it small, so between plus 100 and minus 100. He claims that the contribution could be, that you can disentangle, and it gives me something he calls response functions. So he takes the ratio of a model with normal temperature divided by a model with different temperature, so that I can see the residual, and I can apply those residuals in order to build simple stellar population model with different temperature. It's a zero order, I would say, approximation. Yeah, the justification is that it's to him as well. I agree.
Chiara will be here the rest of the week, so.
Yeah, please come talk. My office is 501. Thank you. Now do I switch off?